Now on the products of powers of tangents and secants here, we're not really going to worry about, different cases, but your trick is going to be to remember that you can replace tangent squared x as secant squared x minus 1, and you can replace secant squared x as tangent squared x plus 1. So let's take a look at this case where both powers are even. Okay, so here, since both powers are even, I can actually take this integral here and I can write it as, I can factor out a secant squared here. So I can factor a secant squared out of secant to the fourth x, and I'll put that with the dx. Okay, and now here's what I want you to think about. See if you can think ahead a little bit. Secant squared x dx is actually the derivative of tangent x times dx. So the idea here is, let's see if we can get this in terms of nothing other than tangents. So to get this in nothing other than tangents, what I would have to do is replace secant squared x with 1 plus tangent squared x, and then, as I said, now that we've got it in all tangents, we can let u equal tangent x, and then du would simply be the secant squared x times dx. So that way this part right here is my du, and then these I can write as just polynomials where I have 1 plus u squared times u squared. So that's what I have. I have 1 plus u squared times du. And then I can distribute the u squared, and I get u squared plus u to the fourth du, and then integrate these with the power rule. You get u cubed over 3 plus u to the fifth over 5 plus a constant. Then replace u with tangent x, and you get tangent x cubed over 3 plus tangent x to the fifth over 5 plus a constant. And there's your final answer for that one. Okay. Now, on the next one, I actually have the secant here is raised to the fifth power, and the tangent is raised to the third power. So in this case, they're both odd. Okay, so what I can do in that case, when they're both odd, is I could actually factor out a secant x from the secant function and a tangent x from the tangent function. So if I factor a secant x and a tangent x out of these two, well, then that will give me a secant x times tangent x to go with the dx. Now, think ahead on me on this one. So remember that that secant x tangent x is actually the derivative of secant x. So on this problem, I'm thinking of letting u equal secant x, so I get this as my du. Okay, so if I'm going to want everything in terms of secant x, then I can think of this, just leave this the way it's written, secant fourth x, and then use my substitution for my identity for tangent squared x here. And we know that tangent squared x is just secant squared x, minus 1. Had to check that real quick. Yeah, so it's secant squared x minus 1. And so now I have secant fourth x times secant squared x minus 1. And so I can let u equal secant x. So if I let u equal secant x right here, then du would simply be secant x tangent x dx. So this part right here is simply the du. And then here I have u to the fourth times u squared minus 1. So here it is, u to the fourth times u squared minus 1 times du. And then multiply that out, and you get u to the sixth minus u to the fourth du, which equals u to the seventh over 7 minus u to the fifth over 5 plus a constant, by just using the power rule on these terms. And then at the end, replace u with secant. And so I get secant x to the seventh power over 7 minus secant x to the fifth power over 5 plus a constant. And so that's how you can deal with powers of secant when they're secant and tangent when they're both odd. Okay, so this problem here, I was going to do it on this video, but I'm going to do this on the next video. So this is secant to the 5th x dx, and so look for it on the next video.